In the second video, horizontal mass spring oscillators, you only needed to watch up until the first 4 minutes for this lesson. The biggest thing that I think that you'll have trouble with is the relationship between angular frequency and period. So let's take a few minutes and review that. Now we revisit angular frequency, only this time it's defined as the square root of k over m. K being the spring constant, how strong the spring is, and m being the mass that's attached to the spring. This formula by itself is not on your formula sheet. However, if you understand the relationship between period, frequency, and omega, then this will make sense to you. If you remember from the first video, we learned that omega is equal to 2 pi, one time around a circle, over t, the period. Well, if we rearrange that a little bit, let's switch the period and the angular frequency. Then what we get is period equals 2 pi over omega. If you take a look on your formula sheet, you will find this formula in the second column. It's the second formula under the list of variables. They also relate it then as it is equal to 1 over the frequency. This combination is very important to remember. Let's continue this train of thought. If we plug in root k over m for omega, that changes our formula to 2 pi over the square root of k over m. Oh, but wait, your math teachers are not going to like that. You've got a fraction within a fraction. So let's rearrange and move the denominator, multiply it by the reciprocal, so we get 2 pi equals m square root m over k. Let's go back to that original formula and approach this from a different direction. If we remember that omega is also equal to 2 pi times the frequency, we can set these equal to each other so that root k over m equals 2 pi frequency. If you play with the numbers a little bit, you'll find out that these two formulas are actually the same formula. All they've done is replace frequency with period, 1 over the period, and then rearrange the formula. In this third video, Mr. Fullerton talks about vertical spring block oscillators. One of the first things he deals with is how to find the equilibrium point of the mass on a spring. And so he starts with a free body diagram where we have the mass on the spring, and then in that we have one force downwards, that's the force of gravity, which is of course still equal to mg, and a force upwards that we'll call Fs, spring force. So, as always, we start with a free body diagram, very important. He then goes on within that free body diagram to set up Newton's laws. Again, as I've been telling you all year long, Newton's laws are extremely important. So here we go. Newton's law, net force in the y direction is equal to ma, is equal to the downward force, which is mg, minus the upward force, which is ky. Now, it really doesn't matter if mg is positive or negative, as long as you are consistent in your motions. By the way, I guess I better mention the ky comes from the fact that Hooke's law says spring force is equal to k times the displacement. Now in the past, we've always used x, but since we're now dealing with the vertical direction, we're going to change x and make it y. All right, so if we are looking for the equilibrium point, that means the point at which the spring comes to rest with the weight on it. Of course, this is going to be longer than the spring when it's without a mass on it. But if we're looking for the equilibrium point, by definition, equilibrium is when the net force equals 0. Therefore, ma equals 0. So now we have 0 equals mg minus ky. All right, if we rearrange a little bit then, what we get is ky equals mg. Now, if we're looking for the length that the spring stretches to come to equilibrium, the new equilibrium point, then we need to get rid of the k by dividing. And so that leaves us with y equals mg over k. Now remember, this y is the equilibrium. This is how far the spring will be stretched when it has the weight added onto the end. At this point in the lecture, Mr. Fullerton went off on this long explanation of finding the period when you have the new equilibrium point. I'm not going to drag you through all of that because in the final analysis, what he decided is once you've established the new equilibrium, you treat it like any other horizontal spring. In other words, the equilibrium becomes the new 0, and any length stretched beyond that is your new x. Let's switch over to the oscillations worksheet now. If you haven't printed it, stop the video and go make yourself a copy. I'm not going to go through all the formulas with you because if you watch the videos, Mr. Fullerton did a great job of showing you examples. Go back and watch his sample problems. However, I do want to point out some things that might cause a problem. On part A, what is the period of oscillation? Well, period is the time for one cycle. So you could look at this and try to guess at 3 point however much seconds per cycle. Or you could just take the total time divided by the total number of cycles, and that would give you the time for one cycle, 3.3. From there, you should be able to get the frequency. Now, amplitude is something we haven't talked about yet. Amplitude is just the height of the wave as measured from the equilibrium point. So it's from the top to the middle, not from the top of the wave to the bottom of the wave. From the very highest point to 0 or lowest point to 0. Letter D should be easy to solve since you have the period from letter A and the mass is given in the information at the top. For letter E, you're using the spring constant that you solved on letter D and the new mass. So now you have K from letter D and a new mass that's given. Find the new period and the new frequency. Letter F asks you to find the position of the block. To do that, you need to go back to the information in the first video about x equals A cosine theta. You now have A, amplitude, and you'll just leave the cosine as it is, cosine of the angle. Alright, be careful on this one because it gives you a lot of information, including that it repeats every half second. Think about what that every half second means. That's a time for a cycle. What is that? Also, you need to watch out for your distances. This gives it in centimeters, but you have to be in meters for this to work. Letter D is the next part that I think may confuse you. It was in the second video, but it was in the part with energy, so we haven't covered it quite yet. When we are looking at maximum force, we want to use Hooke's law, F equals kx. Now, the maximum force occurs at the amplitudes, the maximum amplitudes. So we'll calculate this when x is a. And then to find acceleration, well, what connects force to acceleration? Our old friend, Newton's laws, F equals ma. So those are the formulas you'll use to solve for D and A. D and E. On number 3, I think you should be pretty good to get this one. Notice that it is a vertical stretch, so that 9.6 centimeters is its new equilibrium. So when you get to letter E, the amplitude, you ignore that 9.6. You don't have to deal with that because that's the equilibrium point, which means what is the amplitude if it's pulled down an additional 5 centimeters? Good luck! I will be available tomorrow for tutoring if you need it.